In this explainer, we're diving into something that sounds like it's straight out of science fiction, listening for a whisper from the Earth, a hidden signal right before it shakes.
You know, it's the ultimate question, right? The one that's kept seismologists up at night for decades. Can we find a reliable warning signal before an earthquake hits? For so long, the answer has just been a flat, frustrating no. But what if we've been looking in the wrong place? What if the real warning isn't a tremor, but something totally invisible? Something we can only hear from space? That's what some new research is pointing to, and seriously, it could be a complete game changer. So yeah, let's get into it.
Okay, so the secret here isn't about the shaking itself. It's about this weird electrical hum that seems to happen before the shaking starts. It's this super faint clue that scientists have been chasing for a long, long time, trying to figure out, what is it and where on Earth is it coming from?
This signal is made of something called ultra-low frequency waves, or ULF waves for short. We're talking about electromagnetic signals below 10 Hz. Now, to give you some perspective, the deepest rumbling bass you can possibly hear is around 20 Hz. So this is a hum that is, it's literally too low for us to hear. But here's the magic trick. Because their wavelength is so long, these waves can travel all the way from deep inside the Earth's crust, right up into space.
So how in the world are these signals even made? Well, the leading theory is it's awesome. It's called the geological battery theory. Think about it like this. As all that tectonic stress builds up before an earthquake, it's literally squeezing certain rocks. And when you squeeze these rocks, you wake up these little dormant charge carriers inside them. The rock itself basically becomes a giant, natural battery that generates this huge electric current. And what does a current do? It sends out electromagnetic waves. And voila, that's where our ULF signals come from.
There's just one tiny problem. You can't just stick a microphone in the ground and listen for this hum. There's way too much background noise. So to really hear it, you have to get above all that chaos. You basically need a stethoscope in orbit. And that, right there, is where satellites enter the picture.
All right, so let's look at the evidence. Our first big piece of the puzzle comes from this really groundbreaking study back in 2020. They used data from a French satellite named Demeter, which was, believe it or not, specifically built to look for exactly these kinds of signals.
And these researchers, they did not mess around. We're talking about analyzing 5.5 years of data, looking at more than 5,000 earthquakes. And to be absolutely sure they weren't just picking up static, they were super careful. They only looked at data from the nighttime to avoid noise from the sun, only when the Earth's magnetic field was quiet, and they focused on shallow quakes, where a signal would have the best chance of getting out.
And check this out, this is a real-world example. So the map at the top shows the satellite passing over the Himalayas. The charts below that show all the different frequencies it was picking up. And then, bam! You see that bright spot? That is a clear burst of ULF energy. And get this, it was detected just one day before and right near the epicenter of a magnitude 6.1 earthquake in Bhutan back in 2009.
Okay, so an example like that is pretty jaw-dropping. But in science, one example isn't enough. It could just be a wild coincidence, right? To prove this is a real thing, you need the numbers. You need to show that this kind of signal happens way, way more often than you'd expect just by random chance.
And this is how they did it. It's so smart. On the left, you're seeing a plot of all the ULF signals they found before 5,594 real earthquakes. But then, on the right, they did the exact same thing, but for 5,594 fake earthquakes. Basically, same spots, but at totally random times. And just look at the difference. It is absolutely stunning.
So on the left, with the real quakes, you see those bright hot spots, the red and yellow? That's a huge spike in ULF signals. And they bunch up in two main time frames, about a day before the quake and again around 7 days before. And it's all happening within 200 kilometers of the epicenter. Now look at the fake earthquakes on the right. What do you see? Pretty much nothing, just static, random noise. This was a massive discovery, but as you know, in science, one study is just the beginning. You need someone else to come along and confirm it. So let's fast forward to 2023 and a new study that used data from a different satellite, the China Seismo-Electromagnetic Satellite, or CS. So this new team looked at a completely different set of years, a slightly different group of earthquakes, with a totally different instrument in space. And what did they find? They not only confirmed the first study's results, but they actually added some really cool new details to the story.
For instance, check this out.
They split the data between earthquakes that happened under the ocean and ones that happened on land. And they found something really striking. The sea quakes, on the left, actually produced way more and way clearer signals than the land quakes on the right. The thinking is that maybe the signal just has an easier time getting out through the water.
They also looked at how big the earthquakes were. So on the left, for quakes between magnitude 5 and 6, the signals mostly showed up within about 10 days. But look at the right. For the really big ones, over magnitude 6, the signals started popping up way earlier, like 2 weeks before, and they were spread out over a much bigger area. It's pretty logical, right? The bigger the quake, the bigger and earlier the warning sign. Okay, this plot looks a little complicated, but it's actually super cool. It shows us where the signals are. So the dead center of the circle is the earthquake's epicenter. The rings moving out are distance, 200 kilometers, 400, and so on. And the bright, hot colors, that's where most of the signals were detected. You can totally see this hot ring of activity clustering around the epicenter.
And it gets even crazier and more specific. Because we're talking about electromagnetic signals, they actually get pushed around by the Earth's magnetic field. So for quakes in the northern hemisphere, on the left, the signal hotspot tends to be shifted a little bit south. But for quakes in the southern hemisphere, on the right, it gets shifted over to the east. This is another one of those little fingerprints that tells you this is a real physical phenomenon.
Okay, let's step back for a second. We've got 2 different studies using 2 different satellites separated by a decade of time, and they're finding basically the same patterns. So what does this all mean for the ultimate goal, the holy grail, actually predicting earthquakes? I mean, when you lay it all out like this, the consistency is just incredible. Both studies see signals showing up days to maybe 2 weeks beforehand. Both studies see the action happening within about 200 kilometers, and both agree the bigger the quake, the bigger and earlier the signal. It's a pattern.
Now, this all sounds incredibly exciting, and it is. But, and this is a really important but, we have to be super clear. This is not a perfect crystal ball, not even close. We're still in the very early days of this science, and there are some big limitations.
And this next number is probably the most important one to keep in mind, the one that brings everything back down to Earth, 34%. What does that mean? It means that in that first big study, when they looked at all the major earthquakes, they only found a clear warning signal for about a third of them, 34%. So let's flip that around. That means 2 out of every 3 big earthquakes still happened with absolutely no warning from this method. That's huge.
So here's the real takeaway. For the longest time, we had pretty much 0 potential warning signals. Now we have one that seems to work some of the time. We are literally just starting to learn how to translate the Earth's secret language. The progress is amazing, it's real, but the road to actually being able to reliably predict earthquakes, well, it's still a long one. But it just leaves you with this incredible thought, right? If we're finally starting to hear these whispers, what else is our planet trying to tell us?